let's look at problem C. In this problem, we have several, I would say, numbers, AI, and we need to make them all zeros. Instead of hordes and monsters, I will say numbers. We have numbers A1, A2, etc., n. There are two, and also we store some number x, which is called a combo counter. Yeah. First type of operation is subtract 1 from any number, which is positive. And then we add 1 to the combo counter. The second type of operation is choose some thing which is at least combo counter, and we subtract this combo counter from an. And combo counter is set to 0. You need to find the minimum number of operations to make all zeros. So what we would like to notice is that each operation of the first type, it does two things. It decreases by 1 this number, so the sum is decreased by 1. And also it increases this counter, which also decreases the sum by 1 in the future. So actually the operation of first type kinda decreases the sum 2 times. Does it mean that the answer is like sum over 2 seeding? Answer is unfortunately no. We would like it to be so, and it would be true if you could apply this combo counter to several numbers. So assume, for example, that you have number 3 here and number 6 here, and our combo counter 8. We would totally like to spend this 8 partly on this 6 and partly on this 3 to destroy both numbers. To destroy the 6, for example, and to make 3 a value of 1. But we cannot do that. This means that we need to make the second operation sometimes more than once. This is sad because the second operation, it actually does not decrease sum. Yeah, if we consider this operation, if we consider like the ones destroyed by the second operation, the owner of the first operation, that the first operation added this 1 to x, then second operation does not change the sum. So the second operation not change the sum. So in some sense, we would like to minimize the number of second operations. To minimize the number of second operations, we would like the number x to be as big as possible. For example, what is better? To have x equals 1 and spend 8 times second operation with x equals 1 to destroy this 8. Or we accumulate this x until it is 8, and we make 1 second operation to destroy this 8. The second thing is better, because if you made less second operations, this means you could make more first operations, and you could increase this counter x more. So you would like to make x as big as possible, spend the second operation as rarely as possible, and with as big x's as possible. Okay, because first operation doesn't care which one it decreases, from a small number or from a big number, and the second operation, sadly, it is important for it. So if you consider these thoughts, you may come up with this solution. Let's sort all numbers in non-decreasing order. So these numbers are preferably destroyed with the second operation, and these numbers are preferably destroyed with the first operation. So let's consider our current segment where all non-zero elements live. So all these elements are already zeros, and all these elements are already zeros. Let's think what we would like to do next. So if x is at least an, we would simply like to destroy it. Destroy number an. Actually, we also would like to have one more invariant, which says that x is always no more than an. So this means that we have to have an equality here. If x is an, we just destroy this number, because if we don't, then x will always be greater than an, and we lost. So it's kind of second operation which we have to spend, or the things will go badly. Also notice that it is always a good idea to spend second operation. If you do not do it, you will always have to spend first operations, and actually it will be longer. Yeah, for example, if you do not spend second operation now, you will have to make these many operations, sum of all AIs, to destroy all AIs by the first operation. Instead, like from 1 to n, instead, you can just spend one operation on an and then spend the first operations from 1 to n minus 1. So this is clearly better. This is why you should do it, even if it is possible to avoid. Okay, this is the first case. The second case is if x is less than an. What I want to say is that no need to rush. You don't need to spend this x on any of these numbers. Instead, you can just add 1 to the counter and maybe do this operation later. It will be only great. It would be only better for us. So instead of that, we take our minimum element, decrement it, and increment the counter. This is the solution, a greedy solution. You can consider L and R, and either you destroy the rth element, and R goes here, or you decrement Lth element, and if it is 0, you also go here. Also, do not forget, if you destroy the right element, then x should be set to 0. And if you destroy 1 in the left element, you need to increment x. You shouldn't forget about this. So this is a solution which works in O of sum of AI time. Pretty slow. How can we do it faster? Instead of doing it one by one, we would like to skip a lot of similar terms. Yeah, for example, why do we add 1 here? Subtract 1. Because x is less than an. But if it is less than an, it will likely be less than an for a long time. Yeah, assume that it is 10,000. This is 2. If you make 1 decrement, it will be 3. It's still not 10,000. If you make 10 decrements, it's still not 10,000. You know that you will need at least this number of operations, or formally AR minus X. If you do this number of operations or less, you still shouldn't do the second type of operation. Okay? So let's take minimum of AL and this number. You will definitely want to make so many operations of first type. Why not? So let's do them. Let's say that this is like y. Then what do we do? we say that AL minus equals y and x plus equals y. Then if AL is 0, then plus plus L. And finally, maybe x became at least AR. So if x is AR, then you say that x equals 0 and minus minus R. So you destroyed the rth element with the second operation. Also, you need to like increment the answer. So ans plus equals y here and ans plus plus here. Is that it? No, it isn't. No, it isn't. Because there is one more corner case. Corner case is L equals R. You can check by hand what happens here. Simply, we have one element. What do we want to do? So, you have X and AL. You can make one operation, then the counter becomes X plus 1 and AL becomes AL minus 1. Let's make, I don't know, I operations, then you get this. And if it becomes greater than this, then this is awful, because now you have to finish with all your first type operations. Actually, if X and AL are of different parities, then you have to stop with this condition. For example, assume that X is 4 and AL is 5. Then you cannot make, although this is less than this, you cannot make operation of first type, because it will become 5 and this will become 4. And now you cannot do this. So actually, you stop when this is true, that x plus I is at least this number or this number minus 1. You stop when this happens. Then you make the second type operation, and maybe the first type operation if the parities are different. You can find the formula. It is like I. So let's just find the formula. 2I should be at least AL minus X minus 1. This means that I is at least... No. Like I should be minimum number, which is this. I is... like AL minus X minus 1 half. Is it true? Or AL minus X half. So let's check if my solution says the same thing, because I have a solution. It happened so. No, sorry, actually it doesn't say so. Ah, I understand why. Okay. I think I should build this number. So this is correct thing. But after that, there is an incorrect thing. Namely, if X and AL are of different parities, then we need one more operation of first type in the end. Yeah? For example, if we have 4 less than 5, we destroy it, we get 0 and 1, and you need one more operation to make this 0. So if AL and X are of different parities, actually you need one more operation, and this can be written as this formula. Total number of first type operations is this formula. Also, you need the second type operation, but you do not need it always. Sometimes you do not need it. Why? Because sometimes AL is 1. Actually, when AL is 1, you do not need to do the second type of operation. You simply do the first type operation. So there is a corner case in the corner case. So AL equals 1, then just 1. If AL is at least 2, then you say AL minus X half, ceiling plus 1. Or AL minus X plus 3 half, floor. These are the same numbers. And if L is less than R, then the solution above. You need it. Yeah, so you just store the left border, the right border, and you skip many operations. Why is it fast? It is fast because after each operation you either move L or you move R. So in O of one time, R minus L is decreased by 1. So in linear time, L will become R, and you will stop. So this is how it works.